part A wants us to calculate the entropy change for this reaction, and the information we've got to work with is first that delta H is plus 267 kilojoules per mole, so it's an endothermic reaction, and that the minimum temperature at which it can happen is 1100 degrees C. So the key to that question is going to be to relate enthalpy to entropy, which means we need this equation. Delta G, the free energy change, is equal to delta H minus T delta S. So start by writing that down, because that's the key to all of these kind of questions. And then the point is that at the minimum temperature, that's when delta G goes to 0, because at temperatures below that delta G is positive, so the reaction's not possible, but above it delta G is negative, so then it becomes possible, and that's why it's the minimum temperature. So that's the point at which it swaps from being positive to negative, therefore delta G is 0. So we can say then that delta G is equal to 0 at 1100 degrees C, and we know that that T in the expression is the absolute temperature. So we need to change degrees C into Kelvin, which means we just add 273. Remember, 0 degrees C is 273 Kelvin, so to convert from degrees C to Kelvin we add 273, so that's equal to 1373 Kelvin. And we can therefore say that when delta G is equal to 0, these two terms must be the same, because if delta H equals T delta S, then when you subtract the one from the other, they'll cancel each other out and you'll get 0. We can say delta H is equal to T delta S, and therefore delta H divided by T is equal to delta S, and that's going to be the relationship which will give us what we need, because we know delta H, because it's there, we know T, because it's there, so we can calculate delta S. So that's equal to plus 267 over 1373, which is plus 0.194. Now we have to be careful about units. The units of entropy normally are joules per Kelvin per mole, but because we put kilojoules in here, right, it was kilojoules per mole here, this will be in kilojoules per Kelvin per mole. So we can leave it like that because it didn't specify what units it wanted, but if it had wanted the normal units, which are joules per Kelvin per mole, remember to go from kilojoules to joules, you multiply by 1000. So that would be equal to plus 194 joules per Kelvin per mole. But there was no need to do that because it didn't specify units. However, you must write the unit down. If you just put the number down, that won't do. It's got to be clear what the units are. Part C wants us to sketch this graph of delta G against temperature. These kind of graphs are very important. You're quite likely to get one of these to deal with in the exam. So the key is to remember the relationship, which is that delta G is equal to delta H minus T delta S. So when the temperature is 0, when T is 0, 0 times anything is 0, so that whole term then disappears. So when T is 0, in other words along this line, delta G just equals delta H. So that's very easy, because that means that we know where this line starts, because delta H is up here somewhere at plus 267. So we mark on that point. And we also know that the minimum temperature, which is where delta G is 0, is at 1100 degrees C, which is 1373 Kelvin. So that's the other point we can find, that if this is 1373 Kelvin, we know those 2 points are on the line, and we just assume that delta H and delta S are constants. They don't change with temperature, and so all we have to do is draw a straight line that goes through those 2 points, which is going to look something like that. Okay, so make sure that you know how to deal with graphs like that. The other thing that's interesting about that line, which didn't matter for this question, but which is worth remembering, is that you can see from this, by comparing it with a sort of y equals mx plus c equation for a straight line, that the gradient is equal to minus delta s. And it's just worth being aware of that, because in some questions that can be very useful. Now we need an equation for the reaction of barium oxide with water. So barium oxide, we've got Ba2 plus, because it's in group 2, we've got O2 minus, and therefore the formula is just BaO. Just make sure you get the formulae of these compounds right. And the thing to remember is that there is never any such thing as an aqueous oxide. So if an oxide dissolves, it does so by reacting with the water to form a hydroxide, and you just need to know that that's the case. So we've got barium oxide reacting with water to form barium hydroxide, and again just think about the charges on the ions. Barium is 2 plus, hydroxide you know is 1 minus. So it's not just BaOH, it's BaOH2. And so that's your equation. Doesn't ask for state symbols, so don't put any in. And then it wants to know, if we were to do the same thing with magnesium oxide, what difference it would make. Now the point is that hydroxides, group 2 hydroxides, have limited solubility, and you need to learn the trend, which is that they become more soluble as you go down the group. So MgOH2, with magnesium being higher in the group, is going to be less soluble than barium hydroxide. And if it's less soluble, you'll have a lower OH minus concentration. And if you have a lower OH minus concentration, it's less alkaline, so the pH is lower. And that's the answer to the question. Okay, so it was just, again, a slightly roundabout way of asking whether you knew the trend, which is that the group 2 hydroxides become more soluble as you go down. You don't have to explain it, but you do have to know it.